Hess's Law. Hess's Law is going from a particular set of reactants to a particular set of products. The change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. It uses the first law of thermodynamics. Here are the rules. There are two rules for calculating enthalpy changes for the reaction. The first rule is if a reaction is reversed, the sign for enthalpy is also reversed. And the second rule is the magnitude of delta H is directly proportional to the quantities of the reactants and products in a reaction. If the coefficients in a balanced reaction are multiplied by an integer, then the delta H is also multiplied by the same integer. So here's the deal with Hess's Law. You are given a target reaction. So the sum of all the subsidiary reactions needs to equate to the target reaction. Here's some hints. When you're dealing with Hess's Law, you want to work backwards. In other words, you want to start off looking at the target reaction. What do you have on the reactant side? What do you have on the product side? Okay? And then you can decide if you want to flip equations or you want to multiply the equations by some integer to get the values located or the coefficients located in your target reaction. If you need to reverse any reactions, then you can do that. And if you need to multiply by any reactions, you can also do that. You can also multiply reactions by fractions as long as you are consistent with multiplying delta H by that fraction as well. Here's an example problem. It says calculate the delta H for the reaction. Here's my target reaction right here. Okay? And the sum of all those of this target reaction is made up by these three sub-reactions. Okay, so in other words, it takes, in order to get to this reaction here, it takes 3 steps. Here's step 1, here's step 2, and here's step 3. Now, the sum of all these reactions will give us the delta H for the target reaction. Okay, so first step we're going to look for is we're going to look for coefficients and what's on what side of each side of the equation. Okay, so let's go ahead and erase this real quick. Oops. Okay, so we want to see that we have a CH4 on the reactant side, and I see that I have a CH4 on the reactant side. So I'm good with this equation. Okay. I also see that I have a C2H6 on the product side, but in this reaction I have it on the reactant side. So I'm probably going to flip this equation. Okay? And then I also see an H2 on the reactant side, and I see an H2 on this side. Now everything else should cancel out. Okay? So I should see that the carbon dioxides and the waters and the oxygens all need to cancel out. Okay? In order to cancel out, they need to be on opposite sides of the equation. So here's the solution. Okay? Here's what I'm looking for. Okay? So notice how I flipped this equation, okay, the second equation, and what I'm going to do here is everything should cancel out. Okay, my oxygens need to cancel out, so I have 3.5 oxygens on this side and 3.5 on the other side, which means they'll cancel out. Okay, and next thing I have is I have 2 carbon dioxides on each side of the equation, and the last thing is I have 3 waters on this side, and I have 2 plus 1 water. That gives me 3 waters on the other side, so that cancels out. Everything else should add up, okay, to the everything should add up together to get your target reaction. Okay, so here's my target reaction, and all I'm going to do is I'm going to add up these numbers right here. And when I do that, I get negative 137 kilojoules of energy. Now, this means that this reaction is exothermic, meaning that when this reaction takes place, energy is flowing out of the reaction.